All right, I'd like to welcome you to this session, Practical Guide for Building a 3D Web App from 2D Data. This is the 2020 ESRI Developer Summit. My name is Chris Janekinis. I'll be presenting alongside Raluca Nicola. Just by way of information, this is not a live presentation, as you probably know. We're pre-recording this and distributing it via YouTube. So I'd like to thank you for watching the video. By way of introduction, I am a product engineer on the JavaScript API. I focus mainly on data visualization, smart mapping, and arcade integration. I also have done a bit of work with the geometry engine. I'm based out of Redlands, California. That's where I'm recording from today. My coworker is Raluca Nicola. She is also a product engineer. She focuses on data visualization as well, but mainly on the 3D side. And she will be doing her recording all the way from Zurich, Switzerland. We are not doing this live together. She is also pre-recording. So I will cover the first bit of this talk, and then I'll hand it over to her and she'll finish it off. So what can you expect to learn from this session today? Hopefully the session is the title is descriptive. Basically, we're gonna do a deep dive into 3 different demos. I'll start off doing a sort of a city visualizations demo that will involve 2 separate demos, actually, involving the extrusion of building footprints and also working with 3D models and web styles that come out of the box in the API. Then Raluca will take over and do a deep dive into a train station plan app that she did, as well as a ski resort map. And then she'll wrap it all up with some other examples that you can look at on your own time and explore. So we won't be diving into those ones, but we do want to point you to valuable resources that you can take advantage of. So really what this session is all about is allowing you to take your 2D data sources and be able to build powerful, creative 3D applications. I think a very common barrier to getting started in 3D is a misconception that you can't really do much without 3D layers like scene layers or building scene layers. But that's simply not true. You can take the data that you have today and create some awesome apps. And that's really what this session is all about. It's about inspiring you to go to your workplace and try out a 3D application with your 2D data sources. And some of the high-level overall concepts that are cover probably 90% of the use cases are things like extrusion, using 3D models, whether they're in the API or your own models, being able to render attributes at their proper Z values or elevations based on attribute data. So you may have a 2D layer that doesn't have Z values, but you do have an attribute like a height, or maybe it's a Z attribute field that will allow you to, if you have access to it, be able to render that in Z space. And then being able to do other creative things like creating your own 3D geometries client side. And so we're going to cover all of those topics today. So I'm going to start off and I'm going to do a couple of demonstrations of things that you might find in a city visualization. And that really starts with building footprint data. There's a number of open data portals out there that you can use to find building footprints. Probably the most, I'm not sure if most common is the correct term, but one of the most widely used is the OpenStreetMap data. You can find building footprint data out there that's open to use. And something that you may not know, if I switch over here to my browser, is that ESRI actually provides OpenStreetMap building footprints that are up to date within the last 5 minutes or so, or 15 minutes. It's regularly updated by the minute, and you can bring these layers, these feature layers, into your apps and work with them. So I'm going to show you how to do that in just a minute. And so to give you an idea, this is the REST endpoint for the layer for North America building footprints, and then you have a number of attributes such as the address, and the key attribute here is this height. attribute for building footprints that we'll be working with. So just want to point that out, that you do have access to these free data sources through ArcGIS Online. You also have other ESRI base maps and elevation services and web styles, and I'll dive into what those web styles mean in just a second. As I said, probably the most common scenario for creating a 3D application from 2D is doing extrusion. And the most common, I would say, use case is building footprints. So the way that's handled in the API is by using our 3D symbology. All the visualization capabilities are done with the renderer class, or classes, I should say, and on the most basic sense, it's the simple renderer. And then you have a full set of 3D symbol layers that you can work with. Yeah, we have flat symbol layers and volumetric ones. And because we're dealing with 3D space, we want to use volumetric symbol layers. And when we're working with polygon symbols, that's going to be the extrude symbol layer. And it's really got some pretty basic properties. It's got the material property, which handles the color, even the texture of the, in certain cases. And then you have the size attribute, and that will give you the size in meters that you should be extruding by. And that will always be height in this particular case. You can't extrude by depth or width in a polygon, because those properties are already defined by the geometry itself. And then when it comes to doing that's a static extrusion, which is helpful and useful, but most of the time you're going to probably want to do a dynamic extrusion based on some attribute value, such as the height field in that building's layer, or maybe it's the number of floors, and you want to multiply that by a certain factor because a floor is so many feet or meters. You can certainly do that in using our API. So instead of setting the size in that symbol, you're going to actually use the visual variables property of the renderer. Visual variables are a data-driven way to change the size, opacity, rotation, or color of your objects. And because we're working in 3D, you can simply just set a size visual variable, set the field and the value unit. If you don't set a value unit, it defaults to meters anyway. And that will basically take the value of that height field and extrude your geometry based on that value. So if you have 200 buildings or 2,000 buildings, you'll see various heights based on that data attribute. And I'll show you an example of that. And before I show the live demos, I want to quickly go over Webstyle Symbols. These are 3D models that are provided for free use with the JavaScript API. We actually have 2D and 3D web styles, but because of the nature of this session, I'll focus solely on the 3D ones. What's handy about them is there's not a whole lot of code required to put a pretty complex model inside your application. If you want to use a realistic tree with a particular species, I'm not sure how to pronounce that, Frangola, I would say, you just simply paste that code in that application, as you see there, and you get a nice 3D symbol for just a 2D data source. And otherwise, you might think that that's a complex 3D geometry, but there's nothing that you have to do or worry about in order to get that symbol. And you can, of course, bring in your own custom symbols using GLTF resources, and that's how you would reference it there. I'm not going to show you a GLTF example, but know that if you have a model, you can simply reference it on the href property of your resource in your symbol layer. And then you can scale it and style it how you need to. So I'm going to go ahead and start to show you some demos. Okay, so here is that building layer. I'm going to go ahead and put this into a 3D view, and I'm going to filter it based on just one building, just for demonstration purposes. I'm in downtown Los Angeles. I'm not sure exactly what building this is, but I'm just giving it an orange symbol. So what does that look like in code? I've got my buildings layer. I'm filtering it based on that building. And here I'm setting a simple render, and I'm giving it a flat symbol layer, so a fill symbol with an orange color. Nothing too exciting. That's what you would see in a 2D app. So let's see what happens when we add a volumetric symbol layer. So in this case, I'm giving it an extrude symbol layer. I'm going to give it a gray color. And this edges property allows me to render these nice crisp edges along the kind of the boundary of this polygon as it's extruded. So you get a really nice visualization. And then I'm setting that size to 50 meters. So I'm going to refresh this. And there you see my gray building that's extruded by 50 meters. And those edges are those lines that you see in these corners wherever it changes directions. So that's a pretty straightforward API, I think, for extruding. I'm going to get a little fancier and change this to a different variable starting height. This is simply 100 meters. And it should be twice as tall. There it is. And I've even configured this slider. This is a little hard to see. Let's switch this color to orange, actually. So I'm going to go from gray, just going to say orange. And there we go. Much easier to see. So I have actually set up the slider to show that as I change the extrusion, I can actually see how that would look at different heights, all the way up to 1 kilometer in height. That's a ridiculous height, way too tall in the real world. And this, quite frankly, isn't a super useful sample other than for demonstration purposes, that we can update that height very quickly. And you can see that I'm just taking this slider value and adding it to that symbol and changing it that way. So it's a different demonstration of that. But not super useful. Let's take a look at adding this layer without that filter. So I got this buildings layer, no filter, and this is pointing to that portal item ID for the OSM buildings footprint layer. I'm going to add that to my map, and then I want to take the default render because it has a unique value render of colors based on the building type. And I'm going to change that symbol to a 3D symbol as I iterate through those unique value infos. So instead of having a flat symbol layer, I want to say an extrude symbol layer. I want to give it the same exact color that the original symbol had. I can give it a size of 50, but that size is going to be overridden, and I'll show you why. There's those same edges before, but I'm going to use this visual variable that you saw in that snippet before and set it on the height field and see what I get. So there we go. So you see in the legend here, I got those different building types. It's a nice extrude symbol. And instead of having flat building footprints, I've now got various buildings at their various heights. So as I move downtown, I see taller buildings, and I go into residential areas, I see smaller buildings. Now, when you're working with a huge layer like this OpenStreetMap layer, you're going to notice some performance issues when working with feature layer. So I wouldn't necessarily recommend this when you have a huge data set like this one, but if you work for a small city or a small organization and you've just got a few buildings to work with, maybe a couple thousand or whatever, then you'll have decent performance, and you can be able to render your buildings at their usual heights. So as you can see, it's really not a whole lot of code to get this nice looking visualization. All I had to do was set that visual variable property on my render and ensure that my symbol is a polygon symbol 3D. And we also have an SDK sample that shows this exact same process. So if you just go to the sample page and type extrusion or extrude, then you'll be able to find that sample as well. So hopefully that's given you a little bit of confidence that if you have a footprints layer or you want to take advantage of the OpenStreetMap data, you can add that to your application right now and extrude that data. what about tree data or point data? So I have this 2D data set for tree locations. It's styled based on the width of the tree canopy. And notice that as I zoom in, these sizes are changing so that when I zoom in, it's actually showing the real world space that tree canopy is taking up. The other thing to note is that I'm adding a color visual variable to give it a dynamic, basically to tell a story with the data using color. So in this case, carbon storage. The darker the color, the higher the carbon storage. So this isn't a 3D view, but it's basically a 2D look at the data. Nothing super interesting. You may as well do this in a 2D map. So if we're going to work in 3D, then we want to render these trees with something else. So if you go to the guide in the JavaScript API documentation, and then you navigate down to this reference folder, down a few levels, you see this ESRI Webstyle's 3D page. And we link to this from our documentation as well. You get a full set of icons, as well as different 3D models, such as infrastructure ones. You get power line poles, wind turbines, American football goal, and as well as an assortment of schematic and realistic looking trees, signs. So you get hundreds of symbols available to you out of the box. What's exciting about this is that all you have to do is click on the icon and copy that code to the clipboard, and you can add it to your app, which is what I've done here. I've added this generic tree to that same exact layer. I've changed my base map to a satellite just so it looks a little more realistic. And now I get my data rendered as trees. Not super interesting, as you can see, and they're all the same size. It looks a little odd. You also note that these are multi-layer symbols, or multi-LOD symbols, I should say. So as I zoom in, more detail comes in on those. And you'll see a better view of that in a second. So nothing super interesting, but let's say that, oh yeah, I want to show you the code here to get that. So the trees layer, oh, that's my icon, sorry. Here's my model layer, and the renderer is right here. Carbon renderer, I'm setting my symbol to that other tree style. All there is to it. If I wanted to, I could take any other symbol. Let's just, for kicks, do something ridiculous like this American football goal. I'll copy that, paste it right here. And because I'm auto-casting, I am gonna need to change the snippet just a little bit. So there we go. And almost done. Type web style. And that's American football goal. Let's go back to this application. I'm going to throw it in there. And I should see a bunch of football goals. So again, you get that complex 3D model right out of the box. Let's go back to my previous symbol. Now I want to make something useful of it. So I'm going to add a visual variable, this carbon storage variable. And what that looks like is it's just a color visual variable pointing to that carbon storage field in the layer. And if it's got a value of 0, I'm going to give it a yellowish color, and a dark green I'll say is high carbon, which is 10,000. And so I'm going to save, refresh. I should get those same tree symbols. And now they're rendered by the carbon storage. But this visualization still looks a bit odd because all the trees are the same symbol. And I know that that's not the way it is in the real world. So I'm going to add some other variables, such as the tree height. So that's this, and the tree width and the tree depth. This is an awesome layer because it not only gives me how tall this tree is, but also how wide it is, and in one direction, basically from east to west, and also the width from north to south. Because we're working in 3D, the the object symbol layers that we're working with allow you to stretch and change the size of the variable in different directions, and that's controlled by the axis field. So the axis is height. I'm going to map that to the height field, and because this data is in feet, I need to specify that in the value unit. Same with the width. We have a width from east to west field, and so I'm going to put that on the width axis, and then the depth axis, I'm going to say width from north to south, all in feet. And then I'm going to add this to my renderer, which is here. Sorry, that's the wrong one. And so you see, now instead of having one visual variable, I actually have 4. I have got 3 different size variables, which define the size in 3 different dimensions, or axes, you could say, and then I have that color variable. So when I refresh this layer, I should see a more realistic picture as to what this data looks like. So now I see smaller trees, bigger trees, all based on the real world data as stored in that service. And I've styled them based off of the carbon storage. So you see that the bigger trees hold more carbon than the smaller ones, which makes sense. Now this layer still looks a little odd, and that's because obviously we know that these are not all the same tree species, and some of these are stretched in weird ways. And while I think it is a useful visualization still, but maybe this is more suited for one of those schematic tree styles. So rather than using a realistic symbol, we could use a schematic one. But as you saw before, if I go back to these web styles, you got these schematic trees. So it's probably more suited for this generic one. Let's see what that actually looks like. Name unknown. Thematic tree style. So if I go back to, say, unknown, and then go back to this app, I'm probably going to get something that's more suited for this particular layer. Yeah, I'd say that works probably a little bit better, although it still looks a little, Dr. Seussy in a bit. So, but let's make this realistic. We know that we have a number of realistic tree styles available to us, and I know that I have a field in my service that indicates the species, so I can actually create a unique value renderer to map a particular species of tree to match to that species in my data. And I'll show you what that looks like right here. So I can set up a unique value info, so I have to, and for each info, I get an expected value, such as white oak, and then I have to set a Webstyle symbol to it. And after doing some research, these are done by scientific names. This should match up with white oak, flowering dogwood, Norway spruce, and this doesn't go through all of the unique value infos, but all the major ones in this layer. And then I set it up in this renderer. So I set the type to unique value, the field is common name, is that I'm matching it up with, and I add all of those unique value info. So that's the array of expected values that match to web styles. Pass it in there. I'm going to set a default symbol. So this is just a generic tree. And I'm going to set those same size visual variables to give it that realistic look. And then I'm going to add this to my layer. So instead of using that carbon render, I want to do a realistic one. And I'm going to set a nice pop-up template to say the condition and the height of the tree in feet. And that's all there is to it. Let's go refresh. And there we have it. It's a little hard to see from the satellite image. Let me actually switch it to a light gray base map, gray vector, just so these trees pop out a little bit more. You may be wanting to do something with satellite imagery, and that's fine. But this will give us a better, there we go. So now that those tall, skinny trees actually look like they're more appropriate for that particular species. You see these big wide ones are these maple trees. And as I zoom in to particular areas, I want to see, this is an interesting area back here. You see that the LODs are kicking in, so as I zoom in, I get some nice detail on these leaves and those particular trees. And I get some nice visuals and perspectives, and it's all realistic looking. And what's great about that is that this is all done with 2D data. I don't have to know how to make a complex tree symbol. I don't have to know, I don't have to work with different sizes or different coordinate systems. I just have my 2D data sources. I have good attributes, and then I can use the powerful 3D APIs and the web styles and create some pretty cool visualizations. So hopefully you got inspired as you look through these two demos of how you can take 2D web styles and render point data using them and using realistic sizes as they are in the real world, and also footprints, building footprints and extruding them based on real world sizes. And I would like to then turn it over to Raluca, who's going to go over the other samples such as the train station and the other ones that we have available that we're going to go over. So Raluca, passing it over to you.
Let's now have a look at how you can create a 3D plan of a train station using GeoJSON data, so polygons and points that have floor attributes to create an interactive 3D map. The code is on GitHub, and the live application is also there, but I'm going to show it to you live right now. What you see here are basically also 3D buildings, but what I want to show you is this, actually just the plan, where you can see that we have polygons representing the blue ones, the shops, and then the yellow ones are the platforms, and they are elevated using a floor attribute. So you have the ground floor, then -1, -2, and -3. We're going to be looking at the main features that build this application, and we're going to code these main features in a sample app. So first of all, the elevation info. This is an important concept that comes in very handy when you work in 3D. So you can align features relative to ground, to integrated mesh, to scene layers, or to extruded polygon. There are 4 elevation info modes. The first one on the ground basically drapes the features, and it drops the set values even if they have any, and it will just put these features on the ground. Absolute height is when your features have set values. They don't take into consideration any ground or any integrated mesh layer. They will be displayed at the value that the set property on the geometry indicates. So for example, this icon here is displayed at 30 meters above level 0. The next mode is relative to ground, and this one also keeps the set values, but it does not align them to the level 0, but to the actual layer that is below your feature. So if there's an integrated mesh layer, it will take into consideration the height of that layer at the point where it intersects the feature, and it will also add the set value of the feature. Now, in case you want to align the features to a scene layer, so to buildings, for example, or a building scene layer or extruded polygons, then you should use the relative to scene mode. This again takes into consideration also the set value, and it will just add them up. The next important feature is the fact that you can actually set an expression in your elevation info. And this expression is an arcade expression actually, and it can use attributes from your data. So besides the set values, there is another way to set the height of a feature, and that would be using this feature expression. Now, if you set the expression, this will actually not consider the set values anymore. And in our examples with the train station, let's say we have 2 floors, and the first floor should be at the height of 10 meters and the second floor at the height of 15 meters. We can define this floor expression here, which is an arcade expression, that if the floor attribute of the feature is first floor, then take the elevation of 10 meters. Otherwise, if it's the second floor, take the elevation of 15 meters. And if none of these conditions are met, then just set it to 0. And then once you set it in the elevation info, these values will be passed on to the features. Another nice addition that we made to our symbology in 3D are path symbol 3D layers that now support a profile. So before you could only have a pipe symbol, and since 4.12, I think, we also support a profile of quad. And this allows me in this app, for example, to create the walls for the shops. It's an abstract symbol, but I think it's also very intuitive, more intuitive, so to say, in 3D than just having a simple outline. So let's have a look at the code. As I said, I'm not going to be building the whole app from scratch. I'm just going to show you the main features. So here I have a super simple setup, an index file where I'm linking to the JavaScript and a view div. And this is the menu up here on the right with the buttons. In my main JavaScript file, I am defining a map and then passing it on to a view. The next thing that I'm doing is to define a GeoJSON layer where I'm passing in the data. All the data in this app is in GeoJSON format, and as you can see, it's a polygon with longitude and latitude, and then it has some properties, and one of the properties is the floor. This is what we're going to be using to lift these features up from the ground based on this floor property. I'm setting a definition expression for only 2 floors just to make things easier for the demo. And then as a renderer, I'm passing in a unique value renderer because I want one floor to be to have a yellow outline and the other one a blue outline. As you can see here, then we can differentiate between them better. And next I'm adding it to the map. So this is basically what you see in this view on the right. If the features don't have set values, they will be draped to the ground. And yeah, let's see how we can change that. So in this code over here, I have a mapping that I'm doing. So the name, this is the original name that is in the floor property. This is ground floor, this is level 1. And then I'm setting some values for the relative elevation and the absolute elevation. Relative is basically relative to ground, and absolute will be an absolute height, and we'll have a look at setting both of them. So the first one is relative to ground. I'm adding an event listener to this button over here. Currently it doesn't do anything. But I'm setting here this expression just like I showed you in the slide, and depending on the floor name, I'm setting this relative elevation, so either 10 or 30, and then I'm passing it on to the elevation info on the layer with the relative to ground mode. So now I'm going to be printing the floor expression in the console so you can see it, but let me reload first. So once I hit relative to ground, you can see how these 2 layers are at 10 respectively 30 meters above the ground. This is the feature expression that is being set. And one thing I want to show is this is really aligning everything to the ground. So you can see here how these features are basically not in one plane, and this is not what we want. So we don't want that. A building would never follow the terrain like this. So this is why for our case it's much better to actually use absolute height. Uncommenting this second paragraph here, this is about adding an event listener to the absolute height button, and it's basically the same, just that this time we're using the absolute elevation. So we're going to be using 420 and 440 meters. That's because Zurich is at around 400 meters above the sea level. And then we're setting this expression in the elevation info. Along with the mode, we're changing it now from relative to ground to absolute height. So now when I reload this, and click absolute height, it kind of looks similar, but now you will notice that everything is in one plane, and this is what we wanted. All right, let's have now a look at this other feature I told you about. So here I have the walls layer. The way I generated this walls layer is I imported in ArcGIS Pro the polygons, so the areas, and I used polygon to line, I think, to create a line feature layer from these polygons, and then I exported it as a GeoJSON, and I'm loading it in here. It's really just to add these walls. I'm going to be setting an absolute height expression on this as well, so similar to the polygons. And the next thing that I want to show you is this renderer. So it's basically this path symbol 3D layer with the quad profile and the width of 0.5 meters and the height of 2 meters that gives this impression of a wall. So now you can see these walls. Let me add also the areas. Yeah, this is basically like 2D data turned to 3D. And that's about it with this first demo. Let's move on to the next one, which is a ski resort. So in this map of a ski resort, we're actually creating 3D geometry using a client-side 3D geometry that we call a mesh. So this low poly model here with the triangles is created from a mesh, and I'm going to be showing you how to do that. Then the lines for the ski lifts, we're also going to be looking at that and how to align them to a mesh. And next we'll have a look at these 3D models. These are actually GLTFs, which is a custom format for the web for 3D models. It's very, it became a standard. So you can load it in our API, and you can also like adjust the size and the heading and the position interactively. And I'm going to be showing you how to use the editor widget to make all these small changes. So let's look into the main features now. First of all, how to create such a low poly terrain. Basically, I started with an extent. This is the extent of the Mammoth ski area, and then I'm generating random points for the selected extent. Next, I triangulate the points, and for that I'm using a library called Delonator from Mapbox, which triangulates in 2D, so my points are now 2D. But then I will be using elevation queries on the terrain to get the set values. And additionally, I'm also exaggerating the height 2 times just to give it a more impressive look. And next, I'll be using the Mesh API to create the 3D geometry. So in the end, it looks a bit like this. The next feature is symbolizing 2D points with 3D models. There's not much more to say here. These 3D models, you can download them online, make sure that they have the proper license for that. I took mine from Google Poly. And Otherwise, you could also, I mean, if you know how to create such 3D models, Maya or Blender or any of these software nowadays, they support export to GLTF. And finally, we're going to be using the editor widget to actually modify the geometry, but also to change the height or the heading or the size of the model. So let's dive into the demo. Actually, first of all, before we go into the actual sample app, again, it's just the same as with the previous example. I'm not going to be building the ski resort map from scratch because that would take some time, but I'm using a sample app for it. And before we actually go to the sample app, I have this neat demo to kind of like make you understand how this mesh API works with a super easy example before we dive into the low poly map. So let's pretend that we want to build this pyramid here. This is the Cheops pyramid in Egypt, and I'm just building it with the mesh API. I chose this because it's just like a super simple shape, so it's much easier to understand. Let's hide the ground so that it doesn't distract us. So we have this pyramid here. And the first thing that we start with when we want to build it is with the vertices. V0 is the vertex at the top. These are X, Y, and Z values. And then V1 all the way to V4 are the vertices for the base of the pyramid. And one thing that you'll need to build are the vertex positions, which is basically a flat array of these vertices. So we're breaking it down, like breaking down these arrays into a flat array over here. And next I'm also setting vertex colors because this is like one approach. Another way would be to actually set textures on each of these faces, or you could set colors. You could even set videos if you wanted to. But this is the approach that I used in the low poly map, so that's why I also chose it here in this simple example. So the vertex colors array is again a flat array of the colors that you are using for each of the vertices. These are RGB and alpha values, all between 0 and 255. And you'll be passing these arrays onto the mesh in the vertex attributes property. Now this is all good, but the mesh also needs to know how to connect these attributes, and it does that by setting. You can have multiple components. In this one, I'm only for simplicity, I'm only setting one component, and it has these faces which are made out of triangles. So this would be let me show you visually. This would be like one triangle with vertices 0, 1, and 2. So it takes the values for these vertices from the vertex position. 0, 2, and 3 would be over here, and so on and so forth. And this basically creates a mesh geometry, which is just like point or line or polygon, just that it's in 3D. And to be able to visualize it, you'll pass it onto a graphic. You have to pass on a symbol to be able to see the graphic. But in our case, the symbol doesn't influence the visualization at all. It's just a dummy symbol. And then you pass it on to your graphics layer or to the view graphics to be able to visualize it. So basically, that's a super fast and short intro to the Mesh API. And this will make it easier for you to understand how I used it here. This is now the sample app that kind of shows you the main features of the ski resort app. Again, quite a simple setup, even though here I have a bit more files. This is to create the triangulated mesh and then some utility functions. But basically it all starts here. I'm defining the extent that I want to cut the data in the scene by. I'm creating the map. I'm setting the navigation constraint type to none because I want to be able to like navigate also underground. And then I'm passing the map onto a scene view. Viewing mode local, clipping area is extent. And the next thing that I'm going to do, everything else is commented out, but I'm going to start creating the geometry. I'm not doing anything with it so far, but I will. This function gets called, and this basically goes into this file, and the create geometry function is over here. So the first thing that we do is to create the vertices as random points as a flat vertex array. This is basically just going from x min to x max, y min to y max, and creating a grid to not have this squarish look. So if it would be a grid where every point is set in the center of the grid cell, then I would end up having a very regular squarish look, and that does not look really nice on a low poly. So this low poly should be a bit random. And I'm using here a library that allows me to control the randomness. So it sets a seed, and then basically I get random points, but every time I load this app, the random points will be in exactly that position. So yeah, then I'm just generating this vertices array. Again, it's a flat array, and I'm passing in the x and y values in this grid. I have a few debug functions here that I can use to show you what this actually looks like, because otherwise it's a bit hard to follow, I guess. So these are the points that get generated right now. These are flat points, but they align to the elevation. The next thing that I'm doing is creating the triangles. So again, the mesh will need to know how to connect these points in order to create a mesh. And I'm using the Delonator library from Mapbox, as I mentioned before. Let's have a look at what these triangles look like after the triangulation. All right, so these are our triangles. Now if I remove the ground, so I'm just gonna set the opacity, view.ground.layers.remove all. Now you can basically see these are just 2D triangles, and the next step now would be to enhance them with some set values. So not the triangles themselves, but the actual vertices. So the next method that gets called is this enhance vertices with set values, and we're passing on the vertices. Here we're creating, so these vertices are a flat array. Here we're creating points, an array of points, and we're passing them in a multi-point geometry. The next step would be to use the query elevation method on the elevation layer. So the elevation layer is generated up here from the world elevation service provided by ESRI. So you can go ahead and use this service in your app to have to add elevation layers. And the query elevation method takes in a geometry. It's a multi-point so that I don't have to do it for each single point. And then it will return back this multi-point, but with set values. Next, I'm looping through each point of this multi-point geometry, and P of 2 is basically the set value, and I'm multiplying it by the exaggeration factor to get this exaggerated relief. Next, I'm calculating, here I'm also calculating the min height and the max height of the map, because I will be using it later on in this get color from height method to calculate the interpolated value between a start color and an end color that I'm setting for a corresponding height. And this will be useful when I have to calculate this color position, this vertex color array, that for each vertex I will be able to retrieve a color based on its height. All right, so this returns an array of points enhanced with set values. And going back here, this gets passed into the vertices set value. Here I'm calculating the color array, as I mentioned, and these are switching again to flat vertices that I will then pass into the vertex attributes in my mesh. Just quickly, I'm going to comment this code out to show you what my wireframe mesh looks like now after generating the set values from the elevation layer. All right, so this is my mesh. As you can see, it's way higher above the ground because it's exaggerated, and also the you can see it goes much higher than the actual elevation. So now we're creating the component, passing in the triangles. I'm setting the shading to flat, and I'm passing in a metallic material to be able to have this light reflection, and it kind of like looks like the snow is a bit shiny, so it's just for this effect. And then I'm passing the component into the mesh along with the vertex attributes, and I'm returning that mesh into the main function where I will be passing in onto a graphic. And this is what it looks like. It has some artifacts on the side, but we're not going to bother about those for now. The next thing we want to do is add the ski lift layer. This is a line layer. It does not have any set values. So now when I'm going to add it, you'll see that it's basically showing down here below the ground. And what we want to do is now align it to the mesh. And for that, the mesh utils module has a useful method called create elevation sampler that allows you to create a sampler from a mesh that will allow us to query the elevation and set the set values on a ski lift layer based on that elevation. So now if we check out this function, set values, I'm querying all the features in this layer, make sure that geometry and set values are returned. And then for each feature, I'm densifying the geometry using the geometry engine, because if the feature is not dense enough, then it will only align in those points, like the vertices that it has, and that might not be enough. So I'm densifying it, then I'm querying the sampler, the mesh sampler. I'm querying the elevation and retrieving back the geometry with set values and passing it back on my feature. And then later on, I'm doing apply edits, and I'm updating these features with the new geometry. So now when I reload, you'll see that they align to the mesh. Important to note is that this can be an elevation sampler, so you can do this the same way with the elevation. Now you can see how they align nicely. Now, yeah, as I was saying, so this is using the mesh here, but it works exactly the same if you want to align to your elevation layer. All right, going back now, I'm going to be adding now the models layer. So this is basically for the 3D models. I have a point feature layer here. Initially, it didn't have set values, but I applied the same method that I showed you for the lines to actually get the set values. And then as a render, I have a unique value render, and for each point where the name is chalet, I am setting a point symbol 3D with an object symbol 3D layer, where the resource is a GLTF that I actually downloaded from this website. So I can show you what this looks like. This is Google Poly. I go here quite often. There are some amazing models and great inspiration also for maps. So I took this chalet, and another thing I'm doing is I'm passing in these visual variables. So for the size, I'm driving the size of the model by model size field and the rotation by the rotation field. And I'm also going to comment out this code which adds the editor widget, because I want to show you that once you have these models in your scene, then you can use the editor to actually fine tune and adjust them, like the size and the rotation and all these things. All right, so these are my huts here, my chalets. If I go and say edit feature, so these are feature layers that are editable. That's important to know. Then you see you get these manipulators here, and you could like shift it up and down. You could rotate it, and now notice how the rotation attribute is changing while I do this, or you could resize it. So I made it bigger, and let's say it looks up here. And now once I hit update, this will call the apply edits method, and it will change the values that I have in these fields that are used for the visual variables. Another neat thing is, for example, you notice how here maybe sometimes I have some still, even though I have a lot of vertices now, I still have some that are not really placed the way I would want to. So I can also go and select this layer and then modify the vertices. This will move them up, and then this will move them on the XY plane. I can delete vertices. So yeah, basically with this editor widget or with editing, you can manually create, you could add features or update your features in your scene, yeah, like modify the 3D geometry of it. You can't do this though for the mesh layer. But yeah, this would be it for the ski resort app. As I said, the code is on GitHub. So, here you can find it to study. Like, there's much more going on in this application, as you can see. So, yeah, feel free to check it out there. And now for the final part, I would like to show you some more resources. So, in our SDK on the developer side under JavaScript, we have a lot of samples. These are some samples that show features that we showed to you today. So web styles and using renders and visual variables to drive the height and the color of web styles. Extrusion, extruding polygons. These are basically like samples with small snippets that are super handy if you just need like a small example. And then more complex applications are, for example, the earthquake globe. This is where I'm also using this arcade expression to drive the depth of the earthquake by an attribute, and I'm also exaggerating it 6 times. This is also an example from Christian on how to visualize ocean salinity. Another app would be a hiking app, where this profile is, again, it's built based on the elevation query. or a globe of world population. You can read all about it. We added here these resources, and yeah, just go ahead and check them out. And don't forget to post your questions on GeoNet or just ask us on Twitter directly. Thank you very much.